do want to apologize for something to the group, to the NEOACM folks ahead of time. We originally thought that we were going to do this roles update. We thought we were going to do it in person. And so what the plan was to connect the software that it's a Linux software, runs in a Linux environment and a Unix environment. We were going to connect that our laptop to a projector, and we would be able to walk everyone through the software, running the actual application. And then we realized really just recently that we would not be able to do the software run through live. And I totally forgot that this thing does not run natively on a Mac environment. So I won't be able to show you just the live screens on the Mac because it's a Linux application, and that's just a whole nother thing. So we've taken a lot of screenshots, and I think you're going to be able to get some sense of what's going on from the screenshots. So please excuse the screenshots. And perhaps the next time we get a chance to be together live, we can arrange for a live action kind of demo of the demonstration of what the software is. So what this short talk today is going to be about is the rationale for the robotics challenge, the CSI Clue Robotics Challenge in 2022. As you guys know, we started off with the CSI Clue Challenge, maybe back as early, in the planning stages as early as 2013, and have been talking about it to some degree yearly since that time. And so we are now in 2022, and we are getting ready to talk about how the CSI Clue Robotics Challenge moves forward, keeping in mind that we have a $3,000 or $4,000 robot that the NEOACM has built. And so we don't, it's certainly not my intention to just sidetrack that, sideline that robot, and all the effort that's been put into it. So, we want to keep moving forward. But anyway, I want to give you some idea of what the rationale is, and keep in mind that for the NEOACM members and even community members that might hear this at a future date and time, if you have suggestions or you have input, feel free to contact NEOACM chapter, or you can contact me directly. My email can quickly be found at cameronhughes@acm.org. You can always send me email there. If you have anyone listening to this presentation has some kind of feedback, suggestion, question, or comments, feel free at any time actually to send me an email at cameronhughes@acm.org or at neoacmchapter.org, right? And so that's what this presentation is about. We're going to be talking about the roles, the robot scenario situation editor, and the 2022 challenge for the CSI Clue. So how do I start this? Does it start? Do I just hit a space here? I just hit a space. Okay, let's try it again. Yes, it's up in that box. Okay, so here we are. This is the what you're looking at is the National Robotics Initiative. In 2011, the United States was in the middle of a big race for artificial intelligence robots. President Obama launched the National Robotics Initiative. There was a great deal of promise and a great deal of hype about the National Robotics Initiative. I mean, that's important for our CSI Clue Robotics Challenge, because our CSI Clue Robotics Challenge really grew out of the National Robotics Initiative. So in order for me to really tell you what the rationale is, I have to kind of properly put in perspective, how we, what motivated the CSI Clue Challenge. Why do we even have one? And why should we have one in 2022? And really the beginning of it was the President Obama's National Robotics Initiative, where the goal was to take robotics to a very another level. They were interested in doing co-robotics, having robotics work in the public in a safe and effective manner in medicine, and in government, in the military, at retail levels. There's a very, very big push. And this thing was called the National Robotics Initiative. That's going to be important to remember because we talk about that through a couple of slides here. Here's one of the key headlines: the Obama commanding robot revolution announces major robotics initiative, where the United States president is launching a national robotics initiative to accelerate the development of robots that can help create new businesses and jobs. And that was in 2011. We had one of the key professors that we were working with at the time. This is a quote from the University of Pennsylvania. Let me take that back. We weren't working with this professor. This is one of the professors we followed. Okay, says robotics is a game changer. President Obama's National Robotics Initiative will lead to new innovative technologies that will invigorate America's manufacturing economy by creating new opportunities, jobs. It's going to improve the quality of our life. It's going to revolutionize healthcare, medicine, and it's going to make our nation safer with the development of robots for defense, security, and even emergency response. So this is, what some of the belief system was at the University of Pennsylvania. And iRobot is one of the major vendors of robotics. They have a very large presence in the United States military. They have a large presence in homes in America. They're the people who make the Roomba, a vacuum cleaner robot. So their claim here, investing in robots is more than just money for research and development. It's a vehicle that transforms American lives, and revitalize the American economy, right? So indeed, we are at a critical juncture where we are seeing robot transition from the laboratory to generate new businesses and create jobs and confront the important challenges that we face as a nation. So you can get some idea of the gravitas and the hype that was involved. And we were right in the middle of it. Right at the beginning of it with our CSI Clue Challenge. It's related. That's why I bring up this, just to try to, shake the tree and shake our memories a little bit. In 2013, there was a DARPA Robotics Challenge. And this challenge was really spurred on from the Fukushima nuclear power plant disaster, where we were on the verge of a nuclear meltdown, and human beings couldn't get in and shut things down, and the reactor is going crazy, and it was a very dangerous environment. And that seemed like the perfect application for robots. And tied to that, we had 9/11 that had happened, where we had buildings that came down, and you had all kind of rubble, and that was a very unsafe situation. So DARPA kind of combined those two disasters. And I think there was another very bad earthquake somewhere in the East that was also thrown in. And the idea was to try to solve the problem of search and rescue using intelligent robots. So in 2013, DARPA launched their robotics challenge to spur research and development and investment and really taking robots to the next level. So you had the 2011 NRI, National Robotics Initiative, and then coming on the heels of that, 2013, you had this big DARPA robotics challenge, and NEOACM covered it. We had multiple talks about it. We actually had a correspondent at the actual challenge that did on-site reporting for us. So it was a fun thing. And in 2013, not only was there a robotics challenge, but in 2013, Google bought Boston Dynamics. And And I know you guys recognize this this robot here. It's a commercial version of the Big Dog robot. That was the state of the art. You know, all kind of robot, all kind of research dollars went into this. Actually, millions, I think, actually billions of dollars went into development of this technology. And that robot dog represented the height of robot mobility and robot stability with respect to physical movement. Google bought Boston Dynamics, the company that made that, and Google was betting big on the future of robotics in the United States. And they wanted to, okay, we have John coming in, and they wanted to, you have to admit him here, it says. I guess Julie's going to do that. They wanted to have big control over the robotic scene. And so Google bought the best thing out there. So I guess the military had to at some point publish some of this research, or Boston Dynamics, one of them did. And so that's how Google ended up with that in 2013. Following on, let's see here. On the heels of that, we had the AI open letter. This is very important. That AI open letter happened in 2015. At this point, we're formalizing the CSI Clue Robotics Challenge. We're starting to get it down on paper. The ideas are crystallizing. We have a core group of people that have shown interest. Several of the professors at Youngstown State University were interested in supporting the CSI Clue. Bob Hill at IMDS was interested in supporting the CSI Clue, and at that time, in that context, the Future of Life Institute put out this open letter on artificial intelligence, and they were kind of concerned. They wanted to make sure this artificial intelligence talk and the hype was at a fever pitch by 2013 rather. They were it was at a heightened pitch, and they were concerned about, once you do interviews with these folks, they were concerned with a lot of the black box statistical artificial intelligence that were going on. And so this was a letter to kind of put us on notice and make us realize or be careful or be cautious with respect to artificial intelligence because of the dangers of incorrigibility. And that was really like the nail on the head for the C-test, not the C-test, but the CSI Clue Challenge. We were interested in getting into robots and the co-robotics right from the start because of Obama's National Robotics Initiative. But this OpenAI letter is really the thing that helped us formulate the title, the main thesis, where we were going to compare or do a challenge between classical artificially intelligent robot programming and bio-inspired robot programming. This AI open letter was really the motivation behind that subtitle to the CSI Clue Challenge. So that's where that came from. I just wanted to remind the NEOACM what the background was. NRI was the start, and this open letter was the thing that really made us crystallize on that bio-inspired artificial intelligence versus classical AI. Let's see here. And here's what some of their concern was: the adoption of the probabilistic and decision theoretic representation and statistical learning methods has led to a large degree of integration and cross-fertilization among AI, machine learning, statistics, control theory, neuroscience, and other fields. And because of the great potential of AI, it is important to research how to reap its benefits while avoiding its pitfalls. That probabilistic and decision theoretic and statistical learning methods, those things are largely black boxes in many, many instances. We are still struggling in 2022 to try to find ways to make that type of AI transparent. And the Future of Life Institute was forecasting some of those concerns by letting us know we need to avoid those pitfalls. And they were calling that clarion back in 2015. And if you notice here, I have we have our event poster for the our first kickoff, summer of 2014 at the University of Akron. And if you can see here, we were talking about our robotics challenge and bio-inspired versus classical AI. And so I just wanted to put a pin in this so to bring back into memory what was going on. Also, adjacent to it is our formal cover sheet for our proposal to the National Science Foundation. We applied for funding for this. This is the actual official record. As you can see here, we had CTES Labs was actually the research group, and IMDS is where it was going. There's a date, January the 14th, 2015. There's actually a number, a tax ID number, so a lot of official things here. There's an NSF proposal number here. If you wanted to look that up, you could see what the results of that proposal was. And literally, they encouraged our group, although we did not receive the grant, they really encouraged us to reapply because we got nailed on a formality. The chemist that we had involved on our team, he had his expertise was in the wrong area. He dealt mostly with cells, and when I say cells, I mean battery type cells and energy. That was his research, and they really wanted someone more on the chemical side of things, even though the chemicals that we were talking about were micro scale chemicals and very safe. They still wanted to have another chemist with a different expertise. And that's kind of why we didn't get the funding, and they wanted us to reapply that next year. So this lets you know in 2015, we applied for that National Robotics Initiative grant, and we were applied based off of the CSI Clue challenge that was inspired by the NRI and by that open letter. So, and in 2016, the next year, Tracy and I finished our book on robot programming, a guide to autonomous robots. In this book, I know it's probably not been read by folks in listening distance. Maybe it has. In this book, we advanced our theory in robot architectures that we thought could be used to meet this robotics challenge. That's why we bring this up, because this book really is a encapsulation of all of the things that we had learned from our first book on robotics, plus all of the things we had learned so far in trying to go through the challenge. So the book kind of encapsulates that. And so I just want to put these things in chronological order so you all can see what was going on and why we are where we are and why we are going to go where we're trying to go to. So in 2016, this book comes out. And wow, so in 2017, Google sells Boston Dynamics to SoftBank. So after all of that hype and Google having bought Boston Dynamics in 2013, nothing substantial, no breakthroughs, no miracles happened from 2013 to 2017. And so Google turns around right after recently buying it, and they sold it. And that was supposed to be, you know, the purchase of that was supposed to be the dawning of a new era in artificial intelligence merged with large American capitalism. And so what happened there? And I bring up this point because what we're going to see is that from 2011 to the height almost of the robot frenzy, until 2017, things had started going downhill, and the interest in robotics, or the interest in the hype, was starting to wane. And Google ends up selling Boston Dynamics, right? So that's a interesting thing to note there. But in 2021, right, all is not lost with robotics. In 2021, we have Perseverance. The state of the art, in our opinion, represents the state of the art in robotics. It lands on Mars, along with the sidekick Curiosity. No, Ingenuity was the name of the drone. So Perseverance and Ingenuity land on Mars in February. And those two technologies, as far as we're concerned, represent the true state of the art in robotics. And there's no hype in that at all. These things are on another planet doing what they need to do. And so we go from 2011 with the National Robotics Initiative all the way to 2021 with a significant robotics landing that says a lot about what the state of the art is in robotics. This robot, Perseverance, works nothing like the robots worked in the DARPA challenge. It does not use all of that fancy machine learning and the deep neural networks and deep mind. It doesn't use any of that stuff, and it's on another planet doing its mission as we speak today. So I wanted to point that out to you. And this year, the Congress is sunsetting the funding for the National Robotics Initiative. So the project that President Obama started back in 2011 that was supposed to represent the vanguard of robotics research and a hallmark and to represent opening the curtains on a new day and the dawn of a new time in robotics and artificial intelligence. That funding, the Trump administration did they continued a little bit of it, but each year that program kind of went a little more off the rails. Others will give you a different report. Others will say that it was successful and we met our initiatives and we met our goals. I would just caution you to look around though. We still don't see the robots helping, not in an average way, the elderly in hospitals and assisted living. Although there are some autonomous cars, they're not everywhere like they thought they were going to be. We do use some robots in the military, but nowhere near to the degree that we thought we wanted to. So from my, I guess, empirical point of view, I don't see the results at the level that we thought we were going to get to. So in 2011, it was started, and just this year, they sunset the National Robotics Initiative, so you can no longer get funding for it. Now they're replacing it with something called the Foundational Research in Robotics. That's beyond the scope of this little talk today, and we will leave that for another day. But suffice it to say, it's not the same thing as the NRI. So officially, the NRI is dead. Okay, and so what I'm highlighting here is that we went from hype to reality with this robotics. We went through a lot of stages. A lot of things have come and gone. The Wild We robots that were supposed to be the Robo Sapiens that were supposed to be the coming and the dawning of humanoid robots in the home, that didn't happen. A lot of this stuff petered out, and it's gone. The maker spaces that were also hot, very hot during from let's say 2009 until about 2014 to 2015, those have calmed down and they've basically winded down. Okay, so the real issue is for us, what's the rationale for doing the CSI Clue at this point? Given that the National Robotics Initiative is off, it has sunset, that the maker spaces are no longer doing what they used to do, that the machine learning hype is on the downturn. What is the rationale for this? And And that's what the rest of this brief talk is going to be. I have some things of what we learned during all of this time. We learned that the CSI Clue challenge is extraordinarily complex. And we realized, we saw its complexity on paper, its mathematical complexity, but we have firsthand experience in trying various aspects of the challenge, and we now personally know how complex it is. We learned that it requires multiple mathematical paradigms. So deep learning and neural networks is just really represents a single class of mathematics, the statistical, probabilistic, opportunistic type, in some cases, random brute force methods. That's one class of math. The abstract algebra, discrete mathematics, in some cases, geometrical topology, that's whole different classes of mathematics. And so we realized that in order to meet that challenge, to seriously meet it, it's actually going to require multiple mathematical paradigms. So folks with just, a concentration in calculus and statistics, that's not enough. We found that the robot hardware requires organism of subsystems. And I use the word organism on purpose. Humans are organisms. We're actually collections of systems, and that's kind of where the word organism kind of comes in. An organization of a collection of subsystems. We realize in developing this that these robots will not consist of a single microcontroller with a big program. These things will, by definition and will necessarily be a collection of integrated and intercommunicating subsystems. We also realized that it's going to take advanced power management. I can actually, to my right, I can actually look at one of our robot builds, and it has 3 or 4 serious power sources on it. We also realized that after dealing with students at Akron, students at Kent State, students at Cleveland State, students at Youngstown State, members at the Oak Hill Makerspace, and members at a couple of other makerspaces in Northeast Ohio, dealing with, I think, literally hundreds of individuals. We now know that only highly motivated and competent individuals are going to be able to persevere or even be able to compete in this challenge. At first, we kind of thought there were just people who were just interested or have a passing interest or, mild interest, could get involved and would participate. And we found through interacting with all of these folks, that's just not the case, because the stuff we're doing here is non-trivial. And so don't want to beat that horse, but that's one of the lessons we learned. And then we also learned, because of bullet point number 5, that the challenge cannot be restricted to Northeast Ohio or even the neighboring states, because we had reached out as far as PA, Virginia, and Michigan, and actually had interactions and talks with people from some of those states. And it's just, we're dealing with some hard stuff. And because there was no big money involved, and when people saw that we didn't get that big funding, there was a bunch of folks jump ship at that time too. I won't belabor that. And so anyway, here is what the new challenge will look like going forward. It's going to be a biennial challenge over Zoom, right? So it'll be a Zoom challenge like we're doing today, but it will be live, and we won't allow recorded. Exhibitions, not for the actual challenge. So it'll be biennial. Robot findings, I'll be presented in the Zoom and chat. So you know how you can present questions or responses in Zoom. We have it set up so that the robots will be able to respond over Zoom in the chat with what they found during the actual challenge. We'll talk about those details later. And now we've broken down the challenge. Instead of just having the thing happen on one day, we will have one actual day where the whole challenge happens. We've divided the challenge into 6 parts, and anybody that's interested can turn in each part. That can be turned in a video form, 1 per quarter. for that 2 years. So for each quarter, you can turn in a part of that, your robot going through some phase of the challenge. And so that challenge has been broken down into 6 parts. We can go into that at some later time. And then we're also going to have internet-based judging. So we worked it out so that we could have judges that could be on Zoom and they could watch the live challenge. And we have a mechanism that will actually let them score and judge this thing over Zoom. And so the new challenge is going to be something that happens in a Zoom context. So enough for that. This is what I meant by the book that we wrote actually has in it the methods and the models that we believe can be used to meet that challenge. And we know this because for that last 4 or 5 years, we've been running various aspects of the test ourselves using these methods. And there's 4 methods here. One is called role model. The other one is spaces, stories, etc. One has to do with language level programming. You guys can see what this is: sensor, precondition, postcondition assertions. The scenarios translated into ontologies and reasoning. That stories mechanism is a way to represent reality, to take the real world and describe it mathematically and have it be represented within discrete structures, computational geometry and all that kind of stuff. And then we have a safety component that dealt with the original co-robotics thing. So we actually have these mathematical models. They're in our book. We've been trying them this whole time. And their relevance to today is all of these mathematical methods, they are captured in the ROSE software. So we realized early on that you would have to have some GUI software involved so that the people that were on our team at least would not have to write code in C++ or low-level C or Prolog, which we use a great deal of that. We realized people wouldn't want to program in that, so we took about 2.5, 3 years to develop a GUI user interface that lets you program CSI Clue robots, and more importantly, that lets you interact with these 4 mathematical methods, right? So that ROSE, and I'm only going to take another 5 minutes here. Folks, yeah, because I wanted to keep this short. I don't want to have the folks that we have suffer through this long presentation. I do want to keep, just quickly update you here. We have the Robot Scenario Situation Editor. That's what ROSE stands for. That is an environment that will let the folks that are programming the robot not have to program it in low-level C++, C, or Prolog. Quickly, here's the architecture. It's a multi-tier architecture. We have, if you guys, anybody out in the audience are familiar with a Corba, a request broker architecture, it has a Corba type architecture. The components that you're looking at, the thing called Ralph, that's actually the main Raspberry Pi component. There is a Arduino component here, and right now we show just the logical structure. In reality, where we have 1 box Arduino, you can multiply that. There are 4 or 5 Arduinos involved in this design, and there's 1 or 2 Raspberry Pis involved in this design. And the thing that you see that says rows, stories, spaces, and role, that is going to be a notebook computer or a desktop computer. So you have a computer, 1 or 2 Raspberry Pis on board on the robot, and 4 or 5 Arduinos on board on the robot. And it has a communication between all of these things. And where you see horn clauses, this is the method that all of these devices use to communicate. Okay, horn clauses are used to communicate between the Raspberry Pi and the object request broker. Horn clauses are used to communicate between the object request broker and Arduino, and all of that communicates with the laptop or desktop using horn clauses as well. That's for another story. I guess I want to show that architecture real quick Here's another overview of what this architecture looks like. And this, folks, this is not a future architecture or some robot build that we would like to build. This is the architecture of the robot that we have today, that is running today. Those pink discs, those represent knowledge bases that are, we have one knowledge base on the robot, and we have two knowledge bases that are on the computer that the robot communicates to in real time. I just want to throw this up real quick, that we found that the communication, to do the communication with this robot design, we have TCP/IP. You actually have to SSH a lot. You have to SFTP a lot, and you're doing that during the robot operations. There are serial communications going on at all times. There are Bluetooth communications going on at all times. And there are I2C communications going on at all times on these robots. So there are literally 4 communication protocols happening. And this is not an elaborate, this is one of these bare minimum type communication architectures. So at the communication level, there's a lot of sophisticated things happening. And so this just breaks it out a little bit more. I'm going to post these slides too, for those of you that just might be interested in digging down a little bit more into this. This architecture that actually is the case, not an architecture that will be the case one day. You know, like I said, the robot to my right, it's out of the picture right now, but we ran our last tests, and these are all of the subsystems and components that are running on that robot today. Wow, yeah. And so we do not have time to review this. And folks, and I think you'll be glad that I won't, so I'm going to skip the screen, okay? All right, and you know what, I'm going to show you, like I said, I apologize earlier on. I forgot the fact that we cannot show a live Linux demonstration during a Zoom. So we have a couple of screenshots for you to see what some of these screens capture. This is like the main screen. It divides the kind of programming that you can do into 3 levels. There's direct programming, there's task programming, and there's storage programming. The storage programming represents the highest level. At that point, you're talking to a robot in very high level terms. You know, if the robot is going to be interacting with birthday parties, at the stories level, you're talking to the robot in terms of candles and cakes and presents and, you know, people coming to the party and the birthday guests and all that kind of thing. The task level is a level of programming below that. It describes the same thing, but you go a little more in detail. And direct programming is the lowest level of programming. And any given task you can ask the robot to do, you can decide what level you want to program the robot to do that task in. So this is just like a gateway. You have to define the robot profile, because this thing is designed to actually not just work with the robot we built, but any robot that is based off of a combination of Raspberry Pis, plural, Pi or Pis, and Arduinos, if that's the basic microcontroller architecture, and they're using C++, they can use this environment. These are the basic, this is the basic robot language here. Robot is able to locate, identify, determine, travel, retrieve, put. Basically, any task that you want this robot to do can be a combination of one or more of those verbs right there. And it really does not matter what the task is. Actually, the verb identify, is actually, I think we changed that to determine. So identify is just a subset of that box right there. So anyway, that's like these primitives represent kind of like the visual language of the robot. These are like this is like one of the screens that you might fill in. Right now, our robot only understands these 6 type of geometrical shapes. It knows how to interact with those shapes. You would be responsible for providing, you know, the location of the shape, or you know, what its mass is. The robot's not going to guess how big it is, what its volume is. The robot also is not going to guess in terms of what its material or chemical formulas or those kind of things. And so as a person designing the thing, you would be responsible for filling this in. Here's another thing. As you are describing the robot profile, the robot might have 9 or 10 sensors. Each one of those sensors, you would have to fill out this screen for each one of those sensors, describing the capabilities of the sensors, the limitations, the ranges, units, all of these things. Excuse me for rushing through this. I just want you guys just to get a sense of what some of these screens look like. And like I said, these are screenshots. This is part of a running robot application. We describe attributes of things. And if you notice here, you're going to see numerical values, coordinates, you'll see dimensions, you'll see units. Notice there that we have metal, rubber, plastic, glass. If you were paying attention on the previous screen, you could actually enter the chemical formula. And in some cases, chemical equations to things. The robot understands those things. Travel kind of profile, when you're describing to the robot, when you're describing whether your robot has wheels or whether it has legs or some other kind of mechanism, this thing lets you describe how your robot moves, what the actuator speeds are, what the minimum and maximum, how many motors are involved, how many actuators are involved. Although you don't have to program in C++ or Prolog, you do have to know what your robot is capable of. And in order for the artificial intelligence in our system to be able to do things automatically, it needs this information up front. This is more things where you see the move, the arm, the sense, the decide, the action. Those would actually bring up dialogues that would let you describe in a fairly straightforward way of what you might want the robot to do at a high level without getting into program code. This is an example of one of the lower level screens where you actually are describing whether you want the robot to move in an absolute or relative fashion, whether you want the measurements to be in degrees or radians. Sorry, John, we're not going to use gradients here. Whether you want it to move in centimeters or millimeters. And those boxes where you see servo 1, servo 2, servo 3, you would actually put the actual magnitudes, the actual values that you would want the arm to move. This is like I said, an example of low level. You specify those low level positions, and then the code would translate that into C++ or Prolog. Here's another example of defining one of the components for the robot. Like this right here would allow you to describe if you had a robot arm connected to the robot, or if you had multiple robot arms, this would let you describe each one. Where is the robot arm physically located on the robot? What payload? What's the maximum it can actually lift? What's its volts? What kind of amps are involved? The end effectors, the gripper force, the servo speed, those kind of things, unit speed. When we program our robot, we use these screens. I no longer have to write C++ or Prolog code. I program the robot exclusively from these screens to do, and that's unknown variable tasks. So I don't even need to know what the task is ahead of time. I can sit down in front of this software and program the robot fully from that. We also let the user specify all of the microprocessors and microcontrollers that are involved in their design. What the processor types are, from 8-bit to 64-bit, megahertz, gigahertz, kilohertz, all that kind of stuff. RAM, power requirements. We let them specify what kind of ports. All of this stuff, it gets put into the software because the robot uses all of these, its own information. It uses meta knowledge about itself. It needs to know what kind of sensors are connected to itself. It needs to know what its processors are. It needs to know what its actuators and all of those things are. And the robot uses all of that information to carry out autonomous activity. That's another screen. There's also, I want to point out this time limit. We also give the robot time limits to do tasks. And so when the robot is doing its planning, it considers how much time it has to do the task. It also determines how much energy is going to be required to do the task. So it requires how much energy it has. And so it has that level of sophistication. As much information as we're able to give it, the robot uses that in the decision-making process to do autonomous stuff. And I'm basically just showing you a smidgen of these screens. There are about 90 screens involved here. And so I'm just showing a couple snapshots. And thank you. I'm sorry it took way longer than I thought it would take just to even do this brief overview. Folks, if you all have questions, I'll be glad to answer all the questions you want to give me as long as you want. I'm sorry that it took this long. I thought I was going to be able to go through this in 15 minutes, and clearly I don't know what I'm talking about. But if you all have any questions about any of this stuff, please ask away.
I have a question. You mentioned that, I forget the robot that's on Mars right now.
Perseverance.
Yeah.
Perseverance and ingenuity.
And I know you've done a lot of research on that. You're saying that they're not using any machine learning or deep learning?
No, what I mean is machine learning and deep learning aren't the core programming architectures for those robots. There is machine learning that was used in the design of the robots, like for instance, some of the signal processing that they do, some of those algorithms were a result of machine learning. You know, the reason why they came up with them. But what they don't do is onboard real-time deep learning, if that makes sense to you. Yeah, you know, because that kind of stuff requires a great deal. If you get into deep learning or that kind of machine learning, there's a great deal of human interaction that's involved in that. Processing that data, reprocessing the data, calibrating things, and it's just not doing that on Mars. Now, there are functions that it uses that were created using results of machine learning, but those don't make up the majority of the core of that robot. That robot is really a very classic, is built with classic AI and classic robotics programming.
Okay.
Really bread and butter kind of stuff. The kind of stuff that you see in the factories and in hospitals with surgical robots, that kind of programming, as opposed to the experimental type that we experienced from the 2011 to present.
So are they taking like some of the previous, like the data from, some of the previous robots that were there, and they're using that as a, part of its knowledge base? Oh
yeah. There's a lot of a priori knowledge. Like I actually have the journal book written by the guy that put the robot, the predecessor to this one, on Mars, and that guy breaks it down. He gives you, he was the lead engineer. I think it was for Sojourner. He's the lead engineer for that robot, and he broke it down, these Mars robot programs. He said the last 2 or 3 of them, they had to start over from scratch. And that last one was built exclusively in C++. And they used the knowledge, though. It's not like they threw away the knowledge that they gained from previous missions. Of course, they don't do that. And they use that as a priori knowledge for this thing here. I guess what I'm referring to is that in the sample collection and in the data processing and the computation that's going on in real time on that robot on Mars right now, it is not using DeepMind, AlphaGo type algorithms. That's what I mean.
Are there any elements of like an expert system?
Oh yeah, right. Now if there's any kind of AI on that robot, that's what it's going to be, because that's really the true and tried stuff that we know works, and we know that it'll work on another planet, and there's no There's no mystery. But the issue with the expert system, and you don't want to go too far with that. The issue with the expert system is that the knowledge bases can take up a great deal of space, storage space, if depending on how you implement it. If the expert system, if the knowledge that we're talking about is mathematical equations and mathematical functions, then we're good. If the knowledge base that we're talking about are heuristics, rules, and facts, then there's limited storage space on that perseverance. Not like it's up there with 5 terabytes of storage. If that makes sense.
Yes, thank you.
Could you speak a little bit to the CSI clue? And one thing I was always interested in is knowing, like, you talked about the different things the robots would do inside the software.
Right.
And it seems like the robot wouldn't actually know the layout or where anything is. So it sounds like there's like whatever robots were spun up would have to like initially do like a mapping of the area to like identify the objects and know where they are before it can make any decisions about what to do, because it doesn't make any sense for it to go, hey, look, I found this container, I analyzed it, this is the hazardous one, now what do I do with it? Because it doesn't even know where to take it for quarantine or whatever.
Yeah. Hey, first let me say thanks, Trevor, for those questions. Those are actually really good questions, man. Julie, it is exactly the opposite of that. We are exactly, and this is one of I cannot tell you how many arguments and discussions Tracy had with the people that were interested or not interested in this challenge over the last 6 or 7 years in trying to convey this. On the slides where I mentioned the thing called stories, right? And the acronym basically stands for situations and scenarios translated. What we do with the CSI clue is we take the actual physical situation that the robot is in, the complete physical situation, and we translate that into a priori knowledge. And a priori knowledge just means ahead of time knowledge, right?
Okay, so they have full knowledge of the layout and everything ahead of time. Okay, that's fine. I didn't know, I wasn't aware of that. Thank you for clarifying.
Yeah, that's where the stories come in. And we also have one of those acronyms on the screen with Sarah, and it had to do with robot safety. We don't believe, as a matter of course, that you can have safe robots when robots are involved in unknown environments. I think you're asking for trouble. And so as a part of our whole theory, you translate that situation gets translated in terms that the robot can understand. And let me say just real quick, just for you and Trev, and maybe John, if he's still on, and Lael, as human beings, we learn situational things starting kindergarten, but maybe even sooner than that, right? We learn how to behave at a birthday party. I brought that up. We learn how to behave at a restaurant. We're trained and programmed as young people with scenarios and situations our entire lives. And so when we get into some situation, we largely reason from analogy. People, you get this misconception that we're able to spontaneously do this, that, or the other thing. And that's not true at all. We start running situations from the time we're toddlers and how to behave when we play with other kids, how not to behave, how to behave when mom says stand there, and how not to behave when mom, we learn situations. So our approach to this CSI clue is to give the robots an actual well-defined situation. But even in that well-defined situation, there are incredible challenges. Even if you define the situation precisely, there's still a great deal of very complex challenges there. And that's what's going on. So yes, it's the case that what that stories environment does, the roles environment, some of those screens help you to define what the physical landscape looks like. We also are in the middle of being able to integrate 3D scanners with the software. So where you take a picture of the environment and that, or you scan the environment and that's translated into STL that the robot can process and turn into geometrical, spatial information. So we're looking at that. But yeah, the idea is yep, you have to take the objects that are in the environment, the things that are in the environment, and you have to describe that to the robot. And part of what that software is allowing you to do is capture that. If you're not experienced with doing that, it allows you to capture that. And then you don't also have to know how would you do that in C++ or how would you do that in some of these other languages. We guide you through the questions that you would and the information that you would need to supply in order to provide the map. And the one of the things I wasn't able to show was that the robot also generates for you in return, gives you back a 3D map of the environment, of how it left the environment after it made this change or that change or the other change. You actually get an updated a 3D geometry of what's going on, area map. So yeah, it's that, Julie. You have to. That's what the stories are. Those stories, when we say tell the robot a story, that's the story we're telling it. Here's the situation you're in. It's a birthday party. Here's how many people at the birthday party. There's going to be a table. There's going to be a cake. There's going to be candles. The lights are going to be this, that. And now once you're in that situation, the robot reasons from that knowledge.
So what are the unknowns to the robot? Like what the contents of the containers are?
Right, like what the contents of the containers are. And if you remember, there was kind of a clue kind of element to it, right? Where we had culprits on that had potentially put hazardous chemicals, and we only had clues that would tie the chemical to the culprit. So we only had clues that would tie that. The robots would have to reason about those clues. The other thing was, although the robot knows, the robot would be familiar with what that game board looks like and how it's constructed, how many moves the robot is going to take, right? There was going to be someone rolling dice, remember that kind of thing, and robot would have to have the ability to read what's on some dice, right? Maybe big ones, and then make the appropriate number of moves. That is incredibly challenging, right? And then not only make the appropriate amount of moves, but have enough to know if it can if you remember the game Clue at all, there's a point where if you suspect that someone has committed a crime, you can make an accusation, but you can only make that accusation under certain conditions. We've carried all of that over to the game, and so to the challenge. So the robot has to be able to traverse that board, traverse the board properly, make the accusations at the proper time, make the proper accusations if possible, tie the clues. There's a lot of unknown things. And then there's a part where the robot has to know maybe there is nothing wrong, and maybe I don't even play the game, right? Maybe there is nothing hazardous, right? It can't just automatically play. There was also a component where things might be out of place in the warehouse. I don't know if you remember that description. Things might be out of place, and the robot is responsible for putting things back in place. That sounds so trivial, but oh my God. It's very hard programming.
So you're giving it the scenario, but in that case, you're saying like maybe one of the containers isn't where you told it was. Is that what you're saying?
That's right.
Okay.
That's right. So just so that you remember, this is actually a challenge that involves 3 to 5 robots. So you can't even do this challenge with one robot. One of the robots was just a sentry robot, and that robot's responsibility was to just literally, surveil the warehouse to make sure nothing is missing and everything is where it's supposed to be. That's part of the challenge. And then if something is missing, what's missing? If something is out of place, put it in place. And if something doesn't belong, that robot was responsible for calling the robots that would be involved in doing the chemical or substance analysis and letting them know where to come and that there was an issue. So you had to have inter-robot communication. That robot needed to be able to communicate what the scenario was and to call the robots to come and do the evaluation. And then those robots had to make a determination of whether it was a red, whether it was a go ahead or not go ahead. And if it's a go ahead, those robots then have to communicate their clue to the robot that's actually going to navigate that game board. So there's some ambitious programming in there. Those robots would have to share certain social structures in order to be able to communicate. You just can't have a robot that only knows how to do a route in the warehouse, communicating something to the CSI clue to the CSI team, and that CSI team would need to be able to communicate certain stuff to the robot that going around the board. Yeah, so there was an inner robot communication, and that came from the National Robotics Initiative. That was one of the advancements that the Obama administration wanted robots to be able to make. They needed the robots to be able to communicate with each other, robots that had different functions to be able to share communication, and also those robots to be able to communicate with human beings using non-robotic type communication. So that's like all of those things are in this CSI clue, and they are actually originated from the NRI, the original NRI initiative. So yes, it's some challenging stuff. So that's why we called it a challenge from the beginning, and not a robot competition, because some of the things that are involved are just simply not solved things. And now that the National Robotics Initiative has been a sunset, and we have all of these years behind us, and we've seen all of this stuff, and we have all of this stuff in hindsight, we really, really now have a clear picture of what the state of the art is with respect to the bio-inspired stuff and the machine learning stuff, and what's solved and what's not solved, and what's hard and what's not hard, and why. We have a real clear picture on that right now. So we wouldn't change the actual challenge portion of this, not one iota, because if we solve any of these problems, it's actually you're actually adding to the body of knowledge for robotics program. If that makes sense. I know that's a long-winded answer.
Thank you.
But so in either case, long story short, we think we need to keep going with the CSI clue. We have every intention on doing it. The other aspect of the CSI clue was the CTES Labs component of this. We're doing the research on those mathematical methods and structures, and we were doing that kind of research in 2011 when Obama first came up with that. That's why it was so attractive to us, because we were doing that kind of knowledge representation and problem solving, we were already on that road. So it just really became attractive. So even if you guys could just say, well, hey, folks, we spent $5 grand on a robot. We want to take it and do something else with it. It's not like it doesn't belong to Tracy, and we have our own robots at CTES Labs. We have one that mirrors the one that was built that the NEOACM owns. Our robot is actually more advanced than that one, but our robot was a model for that robot. And so we are going to continue our research. And so I can't say that, we as an organization should keep going. I'm saying that's what the rationale would be. That's how it would work. Tracy and I would want to be on the subcommittee, to continue doing the robotics, right? So we're clearly interested as members there, but that robot does not belong to us. That belongs to NEOACM. And so they could decide to, well, we took a vote and we want to tear it down and use it to build a new bicycle or something. I can't say, if the group wants to do that, we would vote no, but we could be outvoted. We think that it should go forward. We have a way for it to go forward. We've worked it out so that it can be done remotely and using video and using the internet. And frankly, because of how ambitious the programming is, how ambitious the mathematical modeling is, we don't see any way to do it outside of that. There's just the people that we are going to need and need to interact with are probably scattered, in many different climates, time zones.
I know you had tried to get funding in the past. Is that something that the group would reconsider, or even using the method of crowdsource funding, which is a little more, the criteria for doing crowdsource funding is, definitely different than worrying about a grant.
Right. And that, the answer is yes. The answer is yes and no, right? Here's what we learned. When people knew that we had applied for funding, people were out of the woodworks, all over the place wanting to be involved. And then as soon as that did not come to fruition, those people all disappeared. And so what my question would be today, if we had $1 million on the table to do this, you could get all kind of people involved that want to do it so they can get some of the money, but they wouldn't necessarily have the skills that we need to be involved. This is what we did learn, is this is not just warm bodies that agree to participate. These would have to be people that are highly motivated to do this and actually have the skill set to do it. So yeah, sure, I would take funding to do it, but what are you going to do with that funding, right? What are you going to do with it? And as you guys know, all the funding that you guys get, a big part of that funding is people. And giving people money for this and money for that and money for the other thing, and people will quickly stick their hands out and take your money and have nothing in return. And we're past the point where we have trivial contributions to make. We need people that really can bring it to some degree to make some of this stuff happen, right? And so, yeah, the answer is yeah, sure, absolutely, right? But where do you get the people? That's the thing. And if people know there's money, you'll have all kind of people dropping out of the woodworks, and then you have a problem. Well, how do you filter good people from people who are just charlatans and people who really don't have the skill set to do whatever it is? That's to me, that's a dilemma. I don't know, and actually I don't know how to solve that. And so our current plan right now is to post the CSI clue, actually post the challenge, post video of us and our robots doing parts of the challenge, and see if there are people that are just passionate and interested enough to want to get involved and go from there. But if you tell somebody, well, yeah, we got, there's, $2 million funding for this, we'll get all kind of people say, oh yeah, man, I want to be involved. You'll get all kind of people that are interested in being in it at that point. And then you got a people management, what's the answer to that? Leo, that's a good question. What's the answer to that?
I mean, that's hard. I mean, because that's hard. I mean, you already know these kinds of endeavors can be very costly.
That's right.
And so then there could be people who want to participate, but may not have the financial resources to do so. So yeah, you definitely have people who are going to want to get involved just from a financial perspective, but it may be people who would like to get involved, but they just don't have.
They don't have the money. Like if someone had the passion and the skill, or close to the skill, but they had no money, that would be a perfect person that the grant could help. That would be a perfect person for a grant. They have the skill or close to the skill. They have the passion, but they just don't have the robot. Because in this case, in doing this thing remotely, you're going to have your own robot if you're going to compete in this challenge with us, right? Now, if you want to join our group, then you can share the robot that we have remotely in a sense. But the idea of this is that it wouldn't just be us in the challenge. There would be others, and those others would have to find their own financing for their own robots.
Mm-hmm.
And then they would have their own approach.
Yeah, they would have their own approach. Right. We're talking about stories and spaces and role models, but someone else might want to do deep mind and deep learning. And, they may want to say, well, we could solve it with, We can use chat bots or whatever on the internet, and we can get it done. And they're more than welcome to enter into the challenge. And in this case, because we're going to let them do 6 portions of it with video, they use whatever mechanism they want. We don't care.
Mhm.
And we don't care how much they spend on the robot. They can spend $1 billion on their robot if they want to.
I mean, to make a comment on the funding, there is some hardware things that we need as far as that robot. I mean, with the robot that we have that the NEOACM is modeled on, we made a number of changes as far as processors and sensors, and so that robot would need
For
to
the
be-
NEOACM
the NEOACM robot would need to be
updated to match ours.
to match ours,
that's right.
since ours is the prototype that we kind of
Right,
figured stuff out.
right.
So I mean, it's that, and then if at any point where we're actually going to create the stage for the actual event to occur, then we would need money to create the stage and
Right.
print
But
out
that's
the
going to
board,
be,
but that kind of stuff. But
That's minor,
outside
though.
of that,
that's minor. And remember, we realized that, here at our labs, we could just open up our driveway and build the stage right
and
there.
there's
Right,
ways
right,
to
Right.
mitigate.
So it's not like it's going to be something where, oh, we need millions of dollars or hundreds of thousands of dollars. That's just not true. And I don't even want to say that that's
No,
true.
because none of that.
Right, right.
is going
But that's not saying that, oh, well, $1,500 or $3,000 a grant would help. Sure. And at that prototype level, the whole point of what we're trying to do is build something off the shelf. There are $50,000 robot arms out there. There are $50,000 actuators that if we wanted to try to compete at some industrial level. But the whole point that we're trying to make is that we want to show that you can do this in a without spending $50,000. That's the
Right.
whole point. Yeah. Now, if we were going to try to spend 50, then that puts you in a whole different ball game. It's just a whole different deal.
Okay, so it's 7:17, and I would like to thank everybody for participating, and of course, Julie for hosting. Julie is wonderful and always is there for us and setting everything up and us using her account, her Zoom account. She's always wonderful. I don't know what we would do without Julia. We really appreciate her. So I'd like to thank everyone for participating. We're gonna edit this video and it will be posted on Sunday. We will be interviewing Tom Atwood. That's gonna be a very interesting interview, and that's gonna be at 6 o'clock.
And we have to give Julie like an award,
Yes.
like the Zoom Master, the Zoom Master Award, right? Because she's here and tolerates all of this kind of stuff. But anyway, that's an update. We're gonna do a formal update of the CSI Clue rules and the write-up that I don't know if you guys ever seen this, that CSI Clue document is maybe 50 or 60 pages long.
Yeah, so we'll be updating that, and we was gonna post it tomorrow, but it's gonna take a little longer than that. But we will be posting that soon, along with this video and all other videos of the talks we've had this week. So I'd like to again thank everybody. Everybody have a great evening and a great weekend, and hopefully we will see you on Sunday.
Bye now.
Okay,
Thank you.
thank you. Thanks for listening.